We've just talked about the three stationary points: local maximum, local minimum, and stationary points of inflection. There's one more point that we want to investigate. That's called a non-stationary point of inflection. If we have a graph like this, we have this point x1, y1. Clearly, if I take the derivative here, it's not going to be horizontal. My derivative, instead of being 0, is going to be very positive. In fact, this is the most positive, most extremely like this that we have on the whole graph here. So our point will be very, very positive. Well, on either side of our point, if I take a point there and there, our derivatives are still positive. So I have to go from positive to highest positive to positive. And that graph is going to look something like this. On either side of my point in question, I have positive derivatives. If the derivative is above the x-axis, it's positive. On the other hand, if I have a curve like this, this is going to be my most extremely negatively sloped tangent. And that's going to give me a negative. My most negative slope is going to be the furthest away from my x-axis. On either side of the point in question, if I go a little to the left, I have a negative slope. If I go a little to the right, I still have a negative slope. So I have to go negative to most negative to negative. And that's going to be like this. You can see on either side of this point, my derivatives are negative. On either side of this point, my derivatives are positive. Positive because they're above the x-axis in a dy dx versus x curve. Negative because they're below the x-axis in a dy dx versus x curve. We can also make a statement about non-stationary points of inflections. That is, our first derivative at the point in question is not equal to 0. We can see this is the most positive. It's not down here in 0. It's the most positive. We see this is not 0, but it's the most negative point. And let's take a look at the second derivative here. Well, in this case, if I took the derivative of the derivative, or the derivative of the derivative, I'd have a horizontal tangent line at this point and this point. So yes, the second derivative is equal to 0. That's sort of the litmus test for me, is if we have a non-stationary point of inflection. I want to make sure that first derivative does not equal 0, clearly, not equal to 0, not equal to 0, and second derivative must equal to 0. That's a non-stationary point of inflection. To finish off this section on curve sketching, let's talk about global maximums and minimums. We've talked earlier about local maximums and minimums, which were subsets of stationary points when our derivative was equal to 0. For example, here we have a horizontal tangent. We know that f dash of x is equal to 0 there. That's going to be a minimum point. It's going to be a local min because it's not the lowest point on our whole graph. Our lowest point on our whole graph is another point right here. It's something known as a critical values. The critical value is where f dash of x is equal to 0 or f dash of x does not exist. Well, if we have a cusp here, something that looks like this or like this, we can't take the derivative there because our derivatives will be going to vastly different values, meaning positive infinity from this side and negative infinity from that side. So because our derivatives are not going to the same value, at a cusp, we cannot take the derivative. It becomes a critical value. Well, you have to evaluate, where does the first derivative not exist? Where does the first derivative equal to 0 to find out your maximums and your minimums? Here, we have a local max. It's not the highest point of our graph because we've got another point that's higher. It's a local max right here. And again, we see our derivative is equal to 0. Here we have what's called a global minimum. If we restricted our domain from negative 10 to 10, over this domain, we have another spot where the f dash of x does not exist. We have a cusp here. And this will yield a global minimum. Well, the point of all of this is we cannot find derivatives at the endpoints either. We can't draw a tangent at that one endpoint. But we'd have to investigate them if we restrict the domain. Because here, although we can't find a derivative there, the derivative does not exist. It is the global max here. It's the highest point. This is our global maximum. And here, again, our derivative did not exist, and this was our global minimum. And we'd also have to look, this one didn't turn out to be anything. This was just a local max here. This is a local max here at the endpoint. My big point of this whole slide is this. If you're given a graph, you need to know what the critical values are. What are they? It's where your f dash of x is equal to 0. We know how to find that. That's going to give us our minimums and our maximums and our stationary points of inflection. We also have to be concerned with where does the derivative not exist. If you limit the domain, you have to investigate your endpoints to see if they're local maximums or minimums, and also where the derivative does not exist. Often the key with that, if you had, say, y is equal to x plus 1 over x plus 3, for example, call that x squared plus 1 over x plus 3, where does the derivative not exist? Well, set that x plus 3 equal to 0, and that will tell you where you're going to have a vertical tangent, or that's a good spot to show where the problem area is.